Okay, so let's talk a little bit about the formal underpinnings of probability, which have to do with sets. Okay, so let me remind you of the flipping of the 2 coins experiment. Flip 2 coins. Okay, and what were the outcomes? Okay, the outcomes were heads, 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 tails, tails, heads, tails, tails. Okay, those were the 4 possible outcomes. Okay, and the probabilities, okay, were 1/4, 1/4, 1/4, 1/4. Okay, now the set of possible outcomes, we call that the sample space. So the set of possible outcomes we call the sample space omega. Okay. And on this sample space omega, so for every outcome, we have defined a probability. So there's a probability for every outcome. So you can think of that as a probability function P, which takes as input the outcome and produces a probability. Okay? So these probabilities you can think of as being produced by a probability function. Probability function defined on omega. Okay? Interesting. Okay, and so this leads us to the formal specification of the setup for probability. So this pair, which is the sample space and the probability function, which tells you, which assigns to every outcome a probability, these guys together are called a probability space. Okay, now it's a fancy word. You don't need to panic. Okay, the probability space is just the abstract way that we represent the possible outcomes and their associated probabilities from an experiment. Okay, now, of course, the mathematicians can then divorce themselves from the concept of an experiment and just study probability spaces in the abstract. But for our purposes, we're always going to be attached to some experiment. Okay, so the probability space. Okay, it consists of 2 things. It consists of the sample space, omega. It's the set of possible outcomes. And it consists of the probability function, P of omega, which for every outcome in my sample space omega assigns a probability, just like here, 1/4, 1/4, 1/4, 1/4. And there are certain conditions that we require of this probability function. The first is that it is non-negative and bounded by 1. Okay. And that when you add up all the probabilities for your sample space, they must add up to 1. So the sum for outcomes in your sample space of the probability for that outcome must be 1. And just like here, so you have outcomes, you have probabilities, and they all add up to 1, and the probabilities are non-negative and between 0 and 1. Okay, so this is a valid probability space. Okay? And here's the general definition of a probability space. And event epsilon is a subset of your sample space omega. Okay? And so this is just a formal definition of an event, and it's exactly what we already saw. But I'll just point out that because an event is a subset, you can do the things to events that you could do to sets. So for example, consider the event E1 is that you have matching flips. So this consists of the outcomes HH and TT. Let's consider the event E2 that you have at least one head. At least one heads. So this consists of the outcomes HH, HT, TH. Now you can take the intersection event, you can take the complement event, you can take the union event. Okay, so you can say matching flips or at least one head. So epsilon 1 union epsilon 2, or E1 union E2 is matching flips or at least one head. Okay. And this is the union of these 2 events, which is just, which is actually all events. So matching flips or at least one head. You can take the intersection, E1 intersection E2. That would be matching flips and at least one head. So matching flips and at least one head is the intersection. This is just the set HH. And you can compute the probabilities of these sets. You can take the complement of an event, and so on and so forth. So because events are just plain sets, they happen to be subsets of your sample space, You can construct other events by doing set operations on events. So that's just to show you some of the power that can arise from formally viewing the probability space within the realm of set theory, or from the point of view of sets. Okay. Now I want to focus on a special property in this probability space. Okay. Now, don't worry, probability space is just the abstract way of referring to this combination of an experiment where you have outcomes and probabilities. But notice that all the probabilities are the same. And when all the probabilities for all the outcomes are the same, we call it a uniform probability space.